Okay, so color is the result of our vision in response to different wavelengths of white light. So what I'm saying there is that white light contains a number of different wavelengths. Each wavelength represents or presents to us another color. So you can see all the components of white light when white light is refracted. And we always see it in the same order. It's going to be red, orange, yellow, green, blue, indigo, and violet. So indigo is simply another word for a dark blue. Okay, so let's just step back for a second and understand a little bit what I mean when I say refraction. Refraction is the bending of white light, and that's what allows us to see the different components of the rainbow. But how does that actually work? So it has to do with the angle at which you're looking at the light from. Consider that all light moves at the same speed. So what speed is that? The answer is it's really fast, okay? Specifically, light moves at 186,000 miles per second. Now that means that if I were to take, say, a flashlight and turn it on, and that flashlight were strong enough and bound to the rules of gravity in such a way that it would stick to the surface of the earth, if I turned on that flashlight, it would be a matter of a split second. You would see the light hit the back of the flashlight. It would go all the way around the earth and hit the back of the flashlight immediately, instantaneously. And yet that would represent the light actually going around the earth at least 7 times. It would happen in an instant. So that's a long way to travel in an instant, 186,000 miles per second. Another way of thinking about that is that it takes light a full 8 minutes to travel from the sun to the earth. A full 8 minutes is, what would that be, 480 seconds, if I'm doing that math right. 480 seconds, and each second representing 186,000 miles. So light moves very, very quickly. And the thing is that light is in constant movement, and all light moves at the same speed. So your red, your orange, your yellow, your green, your blue, your indigo, violet, it all moves at the same speed and is constantly moving in front of us. And we see it as white light as an accumulation of all of these different colors moving so fast together in front of our eyes. So how do we see them as being separate components? Well, one way to think of this, and this is kind of a silly way to demonstrate this, but imagine that we have, say, let's say we have, can you tell what this is? It's a horse. See, its mane and its tail. Anyway, okay, so let's say we have a horse, and let's say we have a whole bunch of horses. We have a horse that represents red, orange, yellow, green, blue, indigo, and violet. Except every single one of these horses is standing directly in line in front of every other horse. So if we're standing at it and we're seeing all of these horses together, all the time, all we ever see, assuming all of these horses are the same exact size, all we ever see is one horse, because every horse is right behind that previous horse. Light is always moving in front of us as a whole component. There's that horse. That's what we see. We see white light. But if we see those horses move around a track, and they're all moving at exactly the same speed, and they keep going at the same speed, as they turn, we see them all separate if we look at it from a particular angle. So what we're doing when we're refracting light is we're bending white light in such a way that we can see it at a different angle, despite the fact that the light is moving exactly the same distance and at exactly the same speed. So that's refraction. We're bending the light so that we can see the individual components appear to separate simply because of the angle that we're looking at the light from. Okay? Every time you see a rainbow, you see it in this same order. Okay? And if you see, say, what's called a double rainbow, it will still remain in this order, although it might change by flipping, say, upside down. So you might see a double rainbow that goes red, orange, yellow, green, blue, indigo, violet, indigo, blue, green, yellow, orange, red. In other words, it always appears so that this color is always next to that color, always next to that color, always next to that color, and so forth. So this is the visible part of the spectrum. Now, this is the source of all color. In other words, this is sort of light fact, okay? And the reason I say light fact is because color theory is color theory. So this is the fact through which color theory finds its foundation, but this is factual. It'll be a little bit clearer a little bit later why I'm pointing that out as being so important. This is red as we see it and as red truly exists. There is no other red. That is red. That's orange as orange actually exists. There is no other orange. That's yellow. That's green. And so forth. These are the true colors and the source of all color. Why am I pointing out that this is light fact over here with the spectrum? Remember, the spectrum is components of white light. It is light fact. The reason that I say that is because most of the time when we're looking at color in our environment, we're not seeing color directly at its source. We're not looking at the rainbow itself. Instead, what we're looking at when we see color is we're looking at the reflection of light. So what that means is that white light will hit a surface and then it will reflect some parts of that white light, one of these components or some combination of these components, back to our eyes as the viewer. So when you look at, say a color of somebody's shirt, or the color of a backpack, or the color of a table or chair, or whatever it happens to be that you're looking at, what you're seeing is you're seeing the result of pigmentation. A pigment is simply a coloring matter. So if I have, say, a particle of pigment, it could be a natural source, it could be a synthetic source. For example, you could have, say, a pigment of red iron oxide, right? So that's a pigment of coloring matter. Now, that red iron oxide pigment is reflecting back to our eyes a certain color when it is hit by white light. So white light comes down and hits this particular pigment. White light comes and hits this pigment. And this pigment, being a red iron oxide, reflects back to our eyes what we see as being red. That's what we see when we look at it. And anything that's colored with this red iron oxide is going to appear to our eyes as a red. But realize that we're not seeing this pure red in light fact. This is the rainbow. This is where all color comes from. This is the only red that truly exists. That's the source of all red. This red is being reflected back to our eye. That's true. But where are all the other components of white light? Remember, it's white light that's coming down and hitting this pigment. Where are all of those other colors if I'm seeing red? Well, the answer is that all of those other colors are being absorbed. They're not just disappearing, they're all being absorbed into that pigment. You know, when you go out into the sun, you feel like you're getting warm, right? Because light is an energy. Light is being absorbed. You can feel the energy of that light. Light is being absorbed. Now realize this is only the visible spectrum, right? So you've got red, orange, yellow, green, blue, indigo, violet. Well, it's the visible spectrum. The spectrum continues beyond what is visible to us. So for example, underviolet would be ultraviolet. You've all heard that term before. Over red, if we continue the spectrum in the other direction, is what we call infrared. These are continuations of the spectrum, but not the visible spectrum. When you go out into the sun and you start to feel warm, all of those colors are being absorbed into you. Light is being absorbed into you. But the one you have to be careful of is ultraviolet. That's the part of the spectrum that actually burns your skin. So understand that all of these colors are being absorbed or reflected by the pigments in our environment. So even though we see red here, realize that the red that we're seeing is constantly being, what would you say, interfered with, or it is being somehow complicated by the fact that it also contains in that pigment all of these other colors. So we very rarely, if ever, will see a red that is as pure as the red that we see at its source in the spectrum. So that's why color theory is a pigment theory, at least as it applies to art, as it applies to artists, and as it applies to those of us who want to understand how artists use it. Pigment theory is a theory. Although we can say certain truths about the spectrum because that is color fact at its source, when we're talking about pigments and the way that artists use pigments in order to reflect color, they are always using a contaminated version of light fact because they can only be reflecting light through pigments. Now, of course, that's not true if you're talking about artists who are working, say, with light itself, but then you've got an entirely different color theory that applies to the manipulation of light rather than the manipulation of pigment. So we're dealing here with a pigment theory. Artists have to know not just color theory in general, they have to understand pigment theory. Pigments vary. So an artist who is trying to, say, use a pigment to reflect blue is forced to a choice. They have to make a decision as to which pigment they're going to use. There are pigments like ultramarine. Well, that reflects a blue. There's pigments like cobalt. Well, that reflects a blue. There are pigments like Prussian blue, and of course that reflects a blue as well. But each of those pigments reflects the blue, the factual blue from the spectrum, with a different level of intensity. In other words, some blues reflect the blue from the spectrum relatively poorly, and other blues reflect the blue from the spectrum a little bit better. So an artist has a lot of choices to make when they're thinking about the pigments that they're going to choose. So what we're going to do now is we're going to take a look at just the standard color theory. It doesn't take into account all of the different variations that artists have to understand when they're making their choices as to which pigments they're going to use, but it gives a general concept about how pigments interact with each other in a very general sense. So, the standard color wheel. The standard color wheel, as it's usually presented, is a color wheel that starts with, say, a yellow here, and a blue over here, and a red over here. Now, of course, it's a wheel, so it could be, they could go in any one of these spaces, provided that they're in this relationship. So these three colors, yellow, red, and blue, are what we call the primary colors. Now, primary simply meaning first. These are your primary color. So I'll write primary there. I'll just put a P here to save some time. Put a P here. These are our primary colors. Red, yellow, and blue. And because they are the first colors, the primary colors, these are colors that an artist needs to find in a pigment. So they can't mix two other pigments together in order to get these primary colors. They have to have a pigment that reflects this part of the spectrum. So these are your primary colors. Now, in a sense, you could say, because everything else I'm going to do in this color wheel comes from these three colors, you could say that the color wheel only contains these three colors. Now, that's not really true because we're going to use some other words here. But keep in mind that in its essence, the color wheel is red, yellow, and blue, and that's kind of really it. Everything else is a combination. We're never going to add anything other than red, yellow, and blue in some way, shape, or form. So now, between yellow and blue, if we mix yellow and blue together, what do we get? Well, we get a green. Now, understand, green is yellow and blue. You notice I didn't add anything else. I'm just calling the combination something else. So that green is what we refer to as a secondary color. A secondary color is a mixture between two primary colors. So likewise, on this side of the scale, between red and yellow, we would have orange. And between red and blue, we would have, now I know a lot of people want to say purple at this point, but in truth, we call it violet. Okay? Now, the reason we call it violet has to do with the concept of hue, which I'll get to in just a little bit, but this is the term that we use. It's violet between red and blue. These are also secondary colors, mixtures of two primaries. Now, this completes the primaries and secondaries, but we can move on from here. What is between yellow and orange? Well, between yellow and orange, you have yellow-orange. Okay? No other word for it. It's just the same words that are here combined. So you've got a yellow-orange. Between orange and red, you've got a red-orange. Now, notice, why am I saying it as red-orange rather than orange-red? Wouldn't that be the same color? Well, I guess technically it would, but there's a rule here just in the language, and that is that you always say the primary color first. So that's the standard. So we've got yellow, orange, red, orange. Here we would have red, violet. Here we would have blue, violet. Again, the primary color said first. Here we would have blue, green. And here we would have yellow, green. So this tells you what you would get if you were mixing these colors sort of laterally around this form. Between yellow and orange, we would create a yellow-orange. Between orange and red, we would create a red-orange. It doesn't tell us anything about what happens if we mix a red-orange, say, with a blue. It just moves this way around the color wheel at the moment. So these are our primaries. These are our secondaries. And here, what these terms would be called is they would be called intermediate colors. Or they could also be called tertiary colors. Now, I'll tell you, I prefer tertiary, I don't know if you could see that. I prefer tertiary colors here because I prefer to call mixtures between, say, yellow and orange and yellow intermediate colors. It seems to make a little bit more logic, but you tend to have these terms kind of interchanged. So what I mean by that is take a look. These are my intermediate colors, my yellow-orange, my red-orange, my red-violet, blue-green, and yellow-green. Those are my intermediate or tertiary colors. But that doesn't necessarily mean that I have no more possibilities here. What happens if I mix a red-violet and a violet? Well, in that case, I would have in between a red-violet-violet. Okay? We just double up on the violet. What happens if I mix a red-violet-violet with the violet? Well, then I have a red-violet-violet-violet. Okay? And so on and so forth. I could have in between a red-violet-violet and a violet, a red-violet-violet-violet. Okay? And it sounds a little bit silly in some ways, but sometimes you'll even see these written down as exponents. Like, what color are we talking about? I might be talking about a red-orange to the fifth power, meaning red, orange, 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 orange. It sounds a little silly, but if you want to understand color, you have to have a consistent language. And the truth is, there is only one red, orange, 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 orange in the world. There's only one of them, and it looks a particular way. So trying to understand how artists kind of identify colors is understanding a consistent language that they need to be able to understand. So this is your basic color wheel with the placement of your primaries, your secondaries, and your tertiaries, and a couple of intermediates that I've thrown in there. What the color wheel gives us is it creates a color relationship about what happens when we mix colors together, yes, but it also gives us the name of the hues. The hue is a very important concept in color theory, although it can sound a little bit tricky at first. The definition for a hue is the common color name. Now, why is that important? It's important because there are a lot of color names in the world. Like, for example, there are colors like burgundy, which is kind of reddish. There are colors like teal, which is kind of bluish or blue-greenish. There are colors like aqua, which is another blue-green. There are colors like fire engine red, which is an odd thing to call a color. There are a lot of color names out there in the world around us, and even some that sound somewhat common, like there is brown, for example. But you notice none of those color names, burgundy, brown, fire engine red, teal, whatever those colors are, none of those colors exist in a color wheel. It is frustrating sometimes for students in painting to turn to their teacher and say, how do I make a brown? And their teacher says, well, you know, what brown? What kind of brown? There is no brown in the color wheel. There is no tan in the color wheel. There is no beige in the color wheel. All of those colors, even though we have specific names for them in a fashion sense, all of those colors are identifiable and achievable if you understand the basic hues. Hues are the common color name, and these are all of them. All of them. There are no additional hues. So understanding the hue enables us to understand how the colors that are available to us here, and thus the colors that are available to us through the reflection of the spectrum, remember there's no beige in the spectrum either, how these colors can be utilized to achieve those colors that we've put those rather fanciful names to. So these are the hues. Now, consider the fact that if these reflect the spectrum, and if we took all the colors of the spectrum and put them back together, we would get white light, right? If we took the rainbow, put it back together, we would get white light. Well, then it seems to follow that if we took all of these colors and put them all together, we would get white. But the truth is that's not what happens in pigment theory, because in pigment theory, you're dealing with a reflection of the spectrum. You're not looking at the purity of the spectrum, but only a reflection. And because that reflection is happening through pigments, which are themselves contaminated by the fact that they're absorbing other colors, but merely showing one color to our eye, when you mix pigments together, you get a contaminated version of what you would have in the spectrum. So think about the spectrum. You put it together, you get white light. Well, what happens when you put all the colors of the color wheel together? You don't get white, but you get what we would consider a contaminated or lesser version of that. In color theory, we refer to that as a gray. Now, remember, it's not the gray that you say, see in my shirt or see in my hair. It is a gray by virtue of definition. It is a color that has no color quality. In other words, when we look at it, we might see a different version of this depending upon what specific pigments we're using to build our color wheel. Say, for example, if we used an ultramarine for our blue, and we build our color wheel with that ultramarine being the basis for our blue, we would get a different result than if we built the color wheel with a cobalt as being the basis for our blue. They reflect the blue a little bit differently. So naturally, if we mix all these together with one set of pigments that reflect these colors, they would create a particular gray. If we mix this together with another set of pigments that reflect the same hues, but differently because of the pigment variation, we would get a gray as well, but it would be a different gray. So there's not one set gray that looks like the color of this shirt that we're talking about. We're talking about gray as being a color that reflects no color quality. So when we look at that gray in the center, we're not going to be able to say, it's a little yellow gray, or it's a little red gray, or it's a little greenish gray. No, we can't identify the color. In color theory, that's referred to as a gray. Gray is a neutral. We'll talk about that a little bit later too. So now realize what that means. Our color wheel itself tells us what colors we get when we mix laterally around the color wheel. But understanding that this gray happens in the center, if we were to mix all of these colors together, starts to tell us something about what happens when we mix colors across the color wheel. For example, when we mix red with a green straight across the color wheel, what we would get is we'd get a gray. What would happen if we mixed violet straight across the color wheel with a yellow? Well, what we would get is we would get a gray. Now, I want you to understand the logic behind this, because if you understand this, it makes the color theory a little bit easier to get. Remember when I said that the only colors that really exist here, although we've got all these names for the common color names, the hues, all the colors that exist here could really be broken down into just red, yellow, and blue. They're all a variation of a mixture of just red, yellow, and blue. So, what happens when we mix all of these pigments together? We get a gray. What happens when we mix red, yellow, and blue together? Well, then we get a gray. Makes sense, right? Because it's the same thing. So, what happens when we mix red and green together? Well, notice something here. Red is red. What two colors are in green? Remember, green is a secondary color. It's a mixture of two primaries. Red and green is the same thing as saying red and yellow and blue, right? Because green is yellow and blue, so it's red, yellow, and blue. Well, that's the same thing as mixing red, yellow, and blue together, which is the same thing as mixing the entire color wheel together, and so you get a gray. What happens if you mix yellow and violet? Well, remember, violet is what? It's a secondary color. It's a mixture of two primaries. The primaries in question are red and blue. So if we mix yellow and violet, it's the same as mixing yellow, red, and blue. Remember, it's the same three colors, which is the same thing as mixing the entire wheel together. So again, we get a gray. Now, that's a really important concept when it comes to color theory, because it tells us something about what we call the color's complement. Okay? A color's complement is the color's opposite color. So think about how different that is than the way we usually use the term complement when we use that term in ordinary usage. If somebody's wearing, say, a pair of slacks and a blouse, and you say to them, well, they complement each other, what you usually mean is that they go well together. But in color theory, that's not what a complement means. In color theory, it means that they clash with one another. They are the exact opposite of each other. And it's easy to understand why it means that if you simply take a look. Well, yellow, okay, is yellow, and its complement, being the opposite, right across the color wheel, is violet. Violet contains red and blue. I hope you can see that over here. Violet contains red and blue, but it doesn't contain any yellow. So violet is the opposite of yellow. They don't share anything in common at all. So that's why it's considered the complement, because they are the opposites of each other. And two complements mixed together will create a gray. Now, a gray is also referred to as a neutral. So a neutral means that it is no color quality, right? So if I add a violet to a yellow, what's going to happen is the yellow is not going to move laterally around the color wheel, like when I mix a yellow with a green to create a yellow-green, for example, but it's not going to go this way on the color wheel, but it's going to move more towards the center. I add a little bit of violet to my yellow, brings my yellow to right here. If I add a little bit more violet to a yellow, it brings my yellow to right here. If I add a little bit more violet to the yellow, it brings my yellow to right here. In other words, my yellow starts to go down towards a gray. But as long as it's on this side of the color wheel, it's still going to appear to be a yellow, but it becomes a more grayish yellow and a more grayer yellow and a more grayer yellow until those equal mixtures or equal visual mixtures turn it into a color that has no color quality at all. I could say the same if I'm talking about red and green. If I mix green to my red, it goes to here. If I mix more green to my red, it goes to here. It goes closer and closer to a neutral. And that brings in another issue about color that is very important. So let me clear this up and simplify a little bit, and then we'll move on. What I want to do is I want to point out a number of important characteristics of color, okay, that every artist needs to be familiar with. Those important characteristics are actually three. Okay, I've just recently started talking about this second one, intensity. We've already mentioned hue. So the hue of a color is the color's common color name that is found on the color wheel. We've already been over that. The intensity of a color has to do with a color saturation. So by color saturation, we're talking about how much color is in the color, how much of the hue is evident in the color. Now, one of the terms that people will often use when they're talking about intensity is they'll use the term bright. A color is bright, it's intense. But honestly, I think bright is a really bad term to get in the habit of using. Bright is something that in our ordinary usage of our language, we often confuse with light. For example, if you're in a movie theater and you step out of the dark into the day, it's probably just as common for you to say, wow, it's really bright out here, as wow, it's really light out here. And you mean the same thing. You're using the term synonymously. But in color theory, bright and light are two completely different things, and they really don't have a relationship to each other. So it's best to think about intensity as saturation, how much color is in the color. So now we just talked about the fact that if you take a color and its complement, its opposite color, and you add them together, you're bringing both of those colors closer to the center of the color wheel, in which case they become a gray, which we refer to as a neutral. Along with gray, black and white would also be neutrals. Those are colors, yes, but they're not hues. They're colors that have no color quality, meaning they don't reflect any more one or the other a hue as found in the color wheel. They are neutral colors. So when we add a color and its complement, we are taking a color and bringing it closer to a neutral, which means that we're lowering that color's intensity. If I add violet to yellow, it kills the yellow. In other words, the violet is the complement, it is the opposite, it is the anti-yellow. Violet kills a little bit of the yellow, moving it closer to the center of the scale, moving it closer to a gray. It de-intensifies or desaturates that yellow. But the yellow would nevertheless still be a yellow. It's just a desaturated yellow, closer to a neutral. Now, the thing about intensity is this. Intensity, because it refers to saturation, can be affected by adding anything to a color. So, in other words, if I have this much yellow and I add this much of anything else, then obviously the yellow is less by comparison an amount in that mixture. In other words, there is not full yellow now, there is yellow combined with something else. anything you add to a color is going to lower its saturation just by the fact that it makes that color less pure. But understand that certain decisions that an artist could make, for example, if I say I want to make a yellow more neutral, right? I don't want it to be as saturated. And I say, well, I can add anything to it. Well, add a little bit of orange to it, sure. What you're going to get is you're going to get a less saturated color. But you notice if you add orange to it, you're also changing the hue. It moves this way laterally on the color wheel and it turns into a yellow-orange. If I say, well, I'll add green to it, well, it moves this way on the color wheel and turns into a yellow-green. What if I don't want to change the hue? What if I only want to change the color saturation? Well, I can't add another hue laterally on the color wheel without changing the hue itself. If instead I want a less saturated yellow and I want it to remain yellow, I have to add that color's complement. Now, in truth, I can actually do a couple of other things. Because remember, adding a color's complement brings it closer to a neutral, a gray. But there are two other neutrals. There's black and white as well. And I could always add a black to my yellow. I wouldn't change its hue, but I would be changing its saturation. I wouldn't be changing its hue because as a neutral, black reflects no more one part of the spectrum or no more one part of these other pigments in the color wheel than any other. So I could also add a white and I would change the color's intensity. But realize this too, that if I add a black or a white, then I'm changing another important characteristic of color, and that is the color's value. So, what if I want to change a color's intensity? In other words, I want that color to become less saturated. But I don't want to change the color's hue. And I also don't want to change the color's value. I don't want to make it lighter or darker. So, what does an artist do? Now, this is why it's so important for artists and people who are trying to understand what they do to understand something about color theory. I know this is like a rapid fire version of color theory, but I want you to understand the complexity of this. So let's take a particular problem. Let's say, for example, I'm an artist who has a yellow, okay? So I have a yellow in my image, whether it be a drawing, a painting, a print, what have you. I have a yellow in my image. And somewhere else in my image, I'm using the same yellow. And I'm doing that because that creates a kind of color harmony within the image. I'm using the same pigment to create that yellow, and it is repeated within my composition. So my composition is balanced in part because of the use of that yellow. But now I want to make one area that is yellow less saturated. It's drawing too much attention to itself. I want it to be the same yellow so that I can maintain a harmony with the rest of my image, but I want to make this one particular area become less saturated, less intense. What are my choices? Well, I could move to a neutral and simply say adding a neutral will make it less intense. And I add, say, for example, black. And I'm going to find out that my yellow not only becomes more neutral, which was my goal, but my yellow also becomes darker, which was not my goal. I didn't want that to happen. I don't want it to get darker. So I no longer can think about it that way. I no longer can add black to the yellow to make it less saturated. That doesn't work. So instead, I'm going to add, say, another hue, and I add an orange. Well, that makes my yellow turn into yellow-orange, and I've changed the hue. I don't want to do that, right? And then I can say, okay, that's not an option. What if I add the color's complement? Well, adding the color's complement is going to bring it to a less saturated yellow, which is my goal. But there's also in color what's called a local value. All colors in their natural state, in the spectrum anyway, have what we call a local value. So in the spectrum, violet would be darker than, say, yellow. So even though I'm adding the colors complement to the yellow to make it less saturated yellow, I'm not changing the hue, I'm just changing the saturation, but I'm also inadvertently changing its value. Just as adding black makes it darker, adding violet makes it darker as well. So it seems like I'm out of choices here. But if I understand my color theory, I'm not actually out of choices. I could say take my yellow and add it to violet, provided that first I add the neutral white to violet in order to bring violet to the same value as the local value of yellow. In other words, violet is a darker local value. I have to raise that local value to make it as light as yellow's local value by adding the neutral white and then adding that combined violet and white together to my yellow, and I'm going to get exactly what I wanted. I'm going to change the saturation of the yellow. I'm going to keep that yellow in my composition using the same pigment as I did elsewhere in my composition, and I'm not going to change the color's hue, and I'm not going to change the color's value. Complex, yes. But this is what artists have to do. I know that that is fast. I know that that was a very quick overview of color theory, which can be extremely complicated. But understand that there are certain key things that I want you to be familiar with. Most importantly, I want you to understand the complexity or the potential complexity of it. I think too often when people who aren't familiar with color theory or what it is that artists do think about color, they think about it almost like color by numbers. Like what an artist does is they buy the tube of paint that is the blue that they want to use for the sky. And that's really not what happens. What happens is an intimate understanding of how different pigments, varying pigments, reflect the spectrum in different ways and absorb color and reflect color, and an understanding of how the hue of the color, the intensity of the color, and the value of a color is manipulated through mixing in such a way that you get to a prescribed end that doesn't inadvertently create variations in, say, hues and values and intensities that you weren't after. In other words, there is a sophistication to the use of color. I hope you've had the opportunity to download the notes on color theory that I've provided you. Make sure that you're looking over that. If you read through that slowly, refer back to your notes from what I've done here, I think you'll get an idea, if you haven't already, about the complexity and ultimate richness of color theory to artists.